Welcome to yet another episode of Casted, our podcast here from ITU, where we talk about all things related to information technology. So my guest today is Yves Bertot from INRIA and Sophia Antipolis, who is an expert on proof verification, which lies somewhere on the intersection of really foundational mathematics and hardcore software engineering. And the reason we meet today is that he just verified the 1 millionth digit of pi, and I think that's such a great story that I want to place this conversation around this result. So Yves, welcome. So to make sure that our readers or listeners won't be at the edge of their seat the entire conversation, what is the 1 millionth digit of pi?
I don't know. In fact.
You don't know. You just proved what it is, and then you immediately
forgot. And then I forgot about it.
And then you forgot about it. I prepared for this, and it's 1.
Oh, okay.
It's 1. Just like the first digit of pi is a 1, the 1 millionth digit is also 1.
So I was mostly interested in looking at algorithms and the way people think about them. And this was an example of an algorithm that used both some symbolic computing and some facts about real numbers and transcendental functions. So this is why I was looking at this one. You know, the kind of mathematics that are used there are around 19th century mathematics. So it's also a way to understand how much of the mathematics can be described with these automatic or interactive proof tools.
Right, because this is where we want to go, that you have a chance to explain to me what an automatic proof tool or an interactive verification tool actually is. And as you said, the thing you did was to verify the computation following a known algorithm,
yes,
which is 100 years old, or actually a bit older.
I think, people... I've had a hard time understanding because, in fact, I was too lazy to go and look at the papers of Gauss. Mm-hmm. But apparently this algorithm was already described by Gauss. Mm-hmm. And it was rediscovered in the 70s by Brent and Salamine.
In the 1970s?
1970s. So this is basically what I use as my source is... Mm-hmm. Data from articles published by Brent and Salamine on how to compute certain mathematical constants, in particular pi. Mm-hmm. And then there is a book by the Borwein brothers, which is Pi and the AGM, that has the full description of the two algorithms I studied. So this was published in the 90s. So I'm really using, for the algorithmic content, I'm really using information that is already provided in the scientific literature.
So when we say algorithm here, that is both a method of computation mm-hmm. and an argument for why this method is correct.
Yes.
And let's try to disentangle these things, because computing pi is of course something that goes back not only to the 19th century, but probably something like 2,000 years old. Must be one of the early computational problems tackled by mathematicians for millennia.
Yes, I think one of the earliest algorithm is attributed to Archimedes, and what he uses is called like an exhaustion method. He describes polygons that are close to the circle, and so he has a sequence of polygons that are inside the circle where he increases the number of sides. So that it gets closer and closer to the surface of the circle, and he says how to compute their surface using...
Yeah. Maybe just to make sure that we are all on the same page. So the value we want to compute is the circumference, or half the circumference of a circle with radius 1.
Or the surface.
Or the surface, right? Because pi appears in 2 different formulas for...
So this is
that are related with the geometry of the circle.
This is basically how Archimedes describes the value he wants to compute. But more modern presentation actually takes directly the trigonometric functions as the reference, and so and in some way the complex exponential.
Right, but let's stay with Archimedes just for a moment, so that we really understand that. So since it's really difficult to draw the cycle precisely and actually measure this with a ruler, what we can do is to inscribe into the circle a square, for instance, and then
in the case of Archimedes, he starts with an hexagon.
He starts, right, because it's Archimedes, doesn't start with a square. You can put more and more circle-like objects inside the circle, and then use very basic math to compute.
They are regular polygons, and actually starts with this with an hexagon, and then he divides the angles by 2, and he has a simple trigonometric formulae for the sine and cosine of.
And most high school students could do this at home and get a pretty good approximation of pi, at least the first few digits. You could do at home without any help of a computer by just drawing precise polygons inside the circle.
There are only 3 kinds of mathematicians.
There are
those who can count and those who can't.
Yes.
And I can't, that's why I'm in computers. So I don't know exactly what is the value that Archimedes arrives to, but I think it's about 2 digits of precision.
Yeah.
And he does that by starting with this hexagon and dividing until he reaches something that has approximately 100 sides.
I think 96. 96. The 96 gone, yes.
Okay. And he does that for the one inside, and he does the same for the one outside. So in this way, he has a surface that is visibly, by the naked eye, it looks like smaller than the surface of the circle because it's inscribed inside. And it has another one which is visibly, also by the naked eye.
So he gets, right.
So this is his argument to say, I have...
he has increasingly good upper and lower bounds.
I have an interval in which the number and pi has to be.
And his upper bound and lower bound agree on the first few digits, which means that pi must also be squeezed, sandwiched between these 2 values.
So now if you read about modern mathematics, I'm leaving Archimedes. I actually verified Archimedes' method also within my system. So I at some before the paper that I was describing in the talk that you were referring to, I had another one where I did a tour of several methods of computing pi, including the one by Archimedes. And now if we look at what I'm going to use as the modern reference to what is pi, I will take the first positive root of the cosine function and multiply that by 2 and say that this is the constant that I'm interested in. This is pi. And the cosine function itself is going to be defined by a power series. So it's a very close to the kind of process we're accustomed to see in computer science. It's a repetitive process.
But there's already a lot of information in here, right? So I guess for a high school student, the fact that pi can be expressed in terms of a trigonometric function, such as cosine or sine, should not be surprising, because it's a relationship between various angles in these triangles that you can inscribe into the cycle. And then it also turns out that the value of the cosine of x can be described as a sum of increasingly small fractions, which is called the power series expansion. And this is early 18th century math, I guess.
Yes, I think this you said early 80th.
1700s, so it's 18th century. Yeah.
It's at the end of the 17th century and the beginning of the 18th. So that makes that, coming back to pi, there was a Scottish mathematician by the name of John Machin, who just embarked in the computation of the first 100 digits using a simple formula. And I think it must have taken a few days to do it. But, so this method is based on using the arctangent function. And so if you know enough about derivatives and integral, the arctangent function is an object that you can master quite quickly, at least for for its approximations, because the derivative of the arctangent function is an easy to write function. And then from this derivative, you can have easy approximations of the integral, which is the arctangent function. And people knew about that in the 18th century. And I think even the Indian mathematicians knew about it earlier, like in the 15th or the 16th century. But again, my memory fails me, so I can't give names. Foreign names are much harder for me than. John Machen is an easy name to remember for French because it's a joke.
It's a joke?
Yeah, because it's called la formule de machin. Machin is the word that you use for just the thing. A machin is a thing.
Is a thing.
So the formula of so-and-so.
So by cleverly mispronouncing Machen's name, you get a joke. Excellent.
Yeah, and so it
Machen
sticks to memory.
is the advisor of Taylor.
Ah.
Yeah, and so Taylor made this entire project into basically the
Taylor
idea of expressing functions as sums of fractions.
Yes, actually, in the case of Taylor, it's even stronger than that. It's every function of interest is somehow approximated by a sequence of polynomials.
Yeah.
So this is, and polynomials are exactly what computers know how to compute.
Right, but
so
we are still in a world without
this
computers, so we are still in a world where some people like Machen sit down and laboriously by hand compute smaller and smaller fractions and add them by hand. And then after days and days of computation, they finally arrive at the 100th digit of pi.
So this is actually it's the start of an area of human computers. And at that point, people understood that there was a need to hire people just to do computations and make tables.
Right, because we should also understand that until 1950, the word computer refers to a human, a person. So the word computer was a job description of a person. Yeah. And then in the 1950s, the word changes. The word electronic computer refers to what we today call computers, and by 1950 there are no human computers left, so computers are just electronic computers. Rough.
The last big projects using human computers, I have the impression, were both for the NASA effort of the conquest of space, and also because during the New Deal, there was an effort by the government to provide jobs for people who were otherwise unemployed. So some of these jobs were in making like the Hoover Dam or making building highways and bridges. And part of this allotment was used to give a job to people who could compute. So some of the tables that were used in the middle of the 20th century were produced in this way on public money, and it was considered as worthy as producing a bridge.
If you got that wrong, then the bridge fell down. So.
Yeah, well, it's a bit too bad that somehow this kind of human effort got obsolete much faster than the Hoover Dam.
Than the Hoover Dam, nice.
But it still makes that there were quite a few mathematicians that were already working on algorithms because they had to provide the job descriptions for the computers. Yeah, even before they had electronic computers.
Right. So the first algorithms are very much written to be run on humans.
Yeah, and
so there's precise instructions of calculations that are so precise that a diligent, very patient human can follow them step by step, and the right answer comes out.
So this is, in fact, I think algorithmics are part of mathematics forever. But it also makes that algorithmics are in the beginning of computer science, even before computer science was about electronic computing.
Oh yeah.
And when, on a side note, I would like to notice that some of the leaders in this topic were women.
Oh yeah.
So, I think the number 2 person in charge for this project of computation on the New Deal money was a woman. Again, I forgot the name, but people can go and look it up.
So time goes on, and during the 19th centuries, there are increasingly complicated manual computations of pi. Actually, this I looked up. I think the last manual computation gets some 725 digits of pi figured out by hand with pen and paper.
So in France, there is a little anecdote that is quite funny, because there is a place in one of the science museums where the 700 decimals of pi have been computed and written on the wall, but they are wrong starting from a given digit. I don't remember which
excellent.
one.
Yeah, because
so it had to be corrected.
Now we are slowly getting there, because all these computations, of course, are in danger of being wrong.
Yes.
For at least two reasons. One is that the mathematical argument for computing pi, if you want the formula, that could simply be wrong math. And the other could be that even if the formula is correct, the computations involved in following this formula could be mistaken by a simple transcription error, or because somebody was drunk or made a mistake. So
there's no real way of checking. You know, if you make a mistake, there is no physical artifact that will be, because only the first 40 are meaningful for physical.
Okay, right. Because I guess we need this out of the way. We could make a super perfect. We could build in titanium a super perfect unit circle, and then we could, with a very, very good ruler, we could measure the circumference of that, and then we could simply see how long is the piece of string around.
And probably the physical limits of the size of atoms and things like that would make that we would probably not be able to go beyond a few 10 digits.
Yeah, that sounds reasonable.
That may be an overestimation. So, you know, because if you have an approximation of pi to 1,000th, that's pretty good for any everyday life needs. So,
including building bridges and.
Yeah. Then, if you want to do a GPS system that works well and gives you a precise position to build your bridge, in that case, you go a little further, but not that much.
Right, but just mentioning GPS is interesting here, because why would anybody care about this constant? Well, the constant appears in many, many calculations. In fact, some of the early calculations for pi were exactly motivated by, for instance, determining the circumference of Earth. Yeah. So a geolocation, locating people on Earth, are computations that do involve pi. And thanks to GPS, this is something that your phone does now. So getting relatively precise estimates of pi is more than just a gentlemanly pastime, which probably was why the Greeks were interested. Right? The ancient Greeks didn't want to solve any problems. They were just fascinated by the fact that pi and square root of 2 had strange and scary mathematical properties.
Yeah, that may be true, but still, going beyond 40 digits of pi is a futile effort.
From a practical point of view.
So
now we are, at least for the beginning of the conversation, in what seems to be just a gentlemanly pastime where we solve this problem because it's internally motivated.
Yeah, it's like,
how can you not
like going on top of the Everest. Yeah.
Going on top of the Everest, how can you not care about the 1 millionth digit of pi? But so we're getting from this practically motivated math as calculation, which math was for a long time, so just simply figuring stuff out in order to shoot cannonballs in the right direction, or just determining the circumference of Earth. Math then, at the turn of the previous century, takes a completely different direction and becomes a formalist project.
Yes.
And is no longer actually interested in problem solving, but it's fascinated by concepts of truth and logic. Math becomes a part of logic, and logic becomes a part of math.
Well, logic was invented 25 centuries ago, also by the Greek, and it was about basically after the first years of enthusiasm, they discovered that you could use logic in distorted way, and so that went in the sophist direction. Maybe philosophers will, disagree with my understanding of history, but after a while, people distrusted logic because it was too easy to make a big reasoning and then make you understand something that you didn't want. Mm-hmm. And this is because very often you can make people start from false assumptions, and then you make a very reasonable piece of reasoning, and then in the end you make people agree with something they didn't want to.
And logic trains you in focusing on the veracity of the individual reasoning steps rather than questioning the assumptions. Yes. So therefore logic invites you to put your focus on exactly the wrong kind of the argument, which is why some people rejected it. But logic was very much part of a language of an analysis of what the truth is, yes. and the mathematics as calculation was something that was much more of an engineering discipline.
So all of a sudden, with the advent of the end of the 19th century, you start to have people who say, "Oh, but what if geometry was different? What if the initial assumptions of geometry were different?" And this starts to be interesting because physicists are questioning the nature of space. So Euclidean geometry was based on the assumption that parallel lines never meet. But what if they did? And symmetrically, I don't know what is the argument, but a space in which parallel lines do meet corresponds approximately to what happens on the surface of a sphere. So this is something that is enclosed. But if you look the other way around, you may have something that expands as you go further. Mm-hmm. And it turned out that this kind of space would be interesting to understand what is happening with relativity in physics. So all of a sudden, people start to say, "Oh, maybe we can keep the same kind of logic, but we have to question the assumptions differently." And this relativity, in some sense, is hitting hard on everybody. It's not just about physics. Everything becomes relative. And in some sense, the end of the 20th century goes further than that. Everybody starts to think, well, every system of thought is as good as any other. So at some point, we'll have to recover about that. But right now, it's really, well, this is the level, the assumptions that you use. What can we do about that? And well, maybe I don't know if it's completely related, but maybe not. Maybe the thought about the foundations of geometry led people to think that it would be useful to think about the foundations of math at all.
And this was a moral disaster of the highest order for mathematicians, right? That suddenly the foundations of mathematics were drawn into question, and this led to.
I don't know if it's a moral disaster for everybody.
No, not for everybody. Absolutely.
I think a good proportion of them said, "Yeah, but 2 plus 2 is still equal to 4. I can still do a lot of reasoning." I don't know what your foundations are or why you want to think too much about the foundations, but all the other math that I do makes sense. So why should I bother?
Absolutely. But in the other camp, there were people like Hilbert.
And Hilbert did a lot of mathematics in many domains. So it's still, he had the stature to say, "Oh, but this is important. This question is important nonetheless." And he went back into thinking about logic.
And I guess this is at the same time where mathematical logic also became something, thanks to Boole and Frege and so on. Logic suddenly became a piece of math. There was a notation for reasoning about truth statements, and the originally language-based discipline of logic now became a discipline of math where you could manipulate logical propositions with more or less the same approach as you manipulate propositions in geometry.
Yeah, so I think it's also related to algebra. In algebra, you start with computations, and then you think about the process of computation. And in logic, well, you start with the utterances, and then you think about the process of putting the utterances together. So it's very much a language issue, and this is completely revived with the advent of computer science, because on the one hand, people want to develop languages to make sure that the computers do what we want, and on the other hand, we can do all kinds of computations on these new objects, which are
because
the
you
sentences in the language.
Yeah. You mentioned computer science now, because this is, I think, the very surprising result of this very narrow focus on foundations of math that developed around the turn of the previous century, where some people simply said, no, we have to understand the foundations of these things, and spent a lot of time on formalism, which seemed to be highly, almost deliberately impractical. Right? And I think it's a surprise of the highest magnitude that the result of these endeavors turned out to be computer science, which is as practical and impactful as anything you could hope for.
Well, computer science is, well, the way we view computer science now in the beginning of the 21st century is also the result of a very pragmatical approach. That is, we build devices in which we can model small computations by objects that are smaller and smaller, and that we can put in greater and greater numbers, and the complexity of it just escapes the human mind. Unless we give ourselves a discipline of how we put the formulas together. And this is where language plays a role. So we can do that and we start defining programming languages in a way that just practical. You know, if I write this, then it's going to do that. And after a while, we start having a problem that we define a programming language for a given computer and another programming language for another computer. So people start to think this should be somehow, there should be a way to do this once and for all. So your languages start to exist.
But this is middle of the last century, right? 1960s maybe, that the idea that there should be programming languages that are not tied to the individual hardware, to the individual machine, that was a new idea.
Okay,
that took many years.
And people start to think about how you put sentences together and all that. And the mathematicians who are looking at that on the side say, oh, but we could do that with our own sentences. So you go you're in the 60s, and I think McCarthy in the US started this kind of idea, and De Bruyne in the Netherlands started a project that was called Automath. So Automath is very close to my topic, because his own idea was using work in logic by Church, Alonzo Church, directly as the way to represent all the sentences. And there was a tradition also coming from Curry about giving the type of these formulas, and a discovery that if you talk about the type of a formula, no, that's not the type of a formula. If you want to talk about the type of an expression, then this type itself can be an expression.
There was a lot of information here. So do we need to explain types?
So if you think about a program as taking inputs and producing outputs, then what are these inputs and outputs? They may be numbers, or they may be arrays of numbers, or they may be arrays of numbers. So it's very useful to say, to make sure that I'm going to put things together, I will annotate all my programs with this information, what they do take as input and what they produce as output.
This program expects two integers, or a matrix of complex numbers, or a function that maps integers to strings.
And one very simple way to avoid errors in programming is to just make sure that the units correspond. That is, if you have a program that produces a number, then you can feed its output to another program that accepts a number as input.
Because both of these programs are explicitly telling me, by virtue of the formalism, the programming language in which they expressed that this program expects an integer, or this program produces two complex numbers, or a string, or a picture.
So every program say, I eat this kind of thing and I produce that kind of thing. And if you just respect this kind of requirements for every program, then you already avoid a lot of the mistakes that people do when they just put data.
Because, and this is the underlying observation, that programming is an incredibly error-prone process.
Yes.
That is, it's almost impossible to sit down and write a program, even for a highly intelligent person, to write down a program that does what you thought it should do.
Yes. For example, if I write on the board, this is what my computer is going to do, and I ask you to look at it. If I make a mistake in the middle of the board, you won't be able to see it. Most of the time, you won't be able to see it. And so if I reread myself something that I wrote that I said the computer has to do, I won't be able to spot the problems. So I need to have some discipline that helps me say, oh, but this is, you know, like electricians use color-coded wires. Well, we need this kind of color-coded wires when we write the program.
That was a good example. So there are many disciplines that that try to produce stuff that could be wrong, like building bridges or fixing the electricity in a house. And many of these disciplines have actually a default assumption of probably things going wrong. So they have established routines, disciplines, checks, and so on to limit the effect of human error, for instance, by having different colored wires, because we assume that this is something we could easily mess up.
So a lot of people who already know about programming, they are accustomed to use types like, say, this is a number, or this is an array of numbers, or this is a sentence in a language. Now, what I want to do is to be more precise than that. I would like to be able to say, oh, I don't want just any number. I want a number that has extra properties, like it's smaller than the size of the array I'm going to have.
Or it's positive.
Or it's positive.
Even.
Or it's prime.
Or it's prime.
You know.
Right. So, okay, let's just take, so there are some programming languages that completely ignore this, that are very, very weakly typed. Then there are many, many industrial strength programming languages today that have some kind of pretty impressive type system that does what we just talked about. And then you could go another step and say that not only do I want to express the fact that the output of this program is an integer, but it should be an integer that is, say, a prime.
Yes.
Or less than 100.
Exactly. And so this is what, this is the kind of technology in which I made my effort. Using one of these languages that has this capability of decorating the data with even more information. But that extra information is completely described using logic. So if I want to say that a number is prime, I say that there exists no other number that can divide it,
so your computer. So the code of your computer program now is a lot of instructions telling the computer to do first this and then that, but it also includes logical formalisms that express the expected properties of the input and the output of this exact transformation. So you describe not only what you do, but you also describe in logic the properties of what you expect the input to the program to be.
Yes. So there are two ways to do it. One is to say that I have instead of having only 3 colors in my electrical metaphor, I have gazillions of colors, each of which is describing very precisely a property that I can have. And I say my program is taking as input a number which is smaller than 100 and is a prime. And I can hold that. And then when in my program, I say this piece of data, I can feed it to that other program because it requires a number which is smaller than 1,000 and which is a prime. And I can show that being smaller than 100 and being a prime is strong enough for being smaller than 1,000 and being a prime. So I have to do a little logic adaptation to say some of my conditions on my inputs are good for the usage I want to have.
And that part now requires some kind of mini math argument, saying
Yes.
that, for instance, being, what was it?
Smaller than 100.
Smaller than 100 and a prime is enough for being smaller than 1,000.
Yes.
I guess I can prove that in my head. And I also type that into some kind of programming environment.
So you can do that, and for a lot of these conditions, you can do it automatically. So this is where you don't want to spend time on just saying, yeah, everybody knows that 100 is smaller than 1,000, and being smaller than 100 is enough for being smaller than whatever. So this is how we work. We have that, but sometimes we have conditions that are much harder than that. So there is an example by one of the best reference in algorithmics with Don Knuth. And Don Knuth wrote an algorithm for computing all the primes smaller than a given number. And so in this, he builds an array, and he reuses the values in this array until a certain limit. And at some point, we have to be careful that he doesn't reuse values that are beyond the ones that he already put in the array. Mm-hmm. Okay, so that he doesn't take a value that has not been written yet. And so this is a bit of a difficulty. And in his book, he says, oh, I don't need to do this test. I don't need to write anything to test that this mistake won't happen, because mathematically, we know that between n and 2n, there's always a prime number. So he uses a very strong result of mathematics, which is way beyond what can be proved automatically, to guarantee that this piece of software is going to work without a mistake.
His code exploits, probably for efficiency reasons,
yes,
a deep mathematical theorem.
Because that makes it possible to remove a test in his code, and a test that happens in a loop. So you don't want this test to be repeated too many times. And so he says, oh, I can just get rid of the test because it will never be needed. The case where the test fails will never happen. And this is because of a mathematical result.
And the mathematical result we trust somebody else to have proved.
So
and now it gets interesting.
That was conjectured in 1850 something by a French mathematician by the name of Bertrand. Mm-hmm. And it was proved a few years later by Chebyshev.
This is Bertrand's postulate?
Yes, Bertrand's postulate.
Mm-hmm.
And you can prove it on a computer using the same technology as I did. It was done a few years ago by Laurent Théry, a close colleague of mine.
I guess we need to expand that.
To do that, he used a proof that was also found in the book by Erdős, Paul Erdős.
Yes.
So this is an interesting part of the kind of job that we think, is that we don't invent the proofs. We go and get them in the books, and then we translate them in a way that the computer can verify them.
Right, because this is now the system you are building, and the particular system you're building is called Coq. Mm-hmm. There are a number of, maybe a handful of different research groups around the globe that try to build these. So this is an automated interactive theorem prover, or what is the correct terminology?
I think the word is mostly interactive theorem prover.
Interactive theorem prover.
But they all rely on some level of automation.
Which is an extremely precise, so this is both a syntax for expressing mathematical statements, mm-hmm, and so it's a formalism, and it's a syntax for expressing mathematical reasoning steps, such as if I want to prove that P implies Q, then I first have to assume P, and then I have to do some math, and then I have to end at Q. Mm-hmm. So these reasoning steps are built into the system, and then I, as a mathematician, can sit down and write my proof so that it is verified step by step by a computer, as opposed to the normal way for a mathematician to operate, which is to write down the proof in English using somewhat more flowery prose, and maybe
it has
elegance.
To be flowery because you want other humans to read it.
I want other humans to read it, right? And then publish that and wait for some other mathematician to go to the proof and say, yes, I'm convinced because these kinds of arguments normally work, and I'm not actually going to check that computation, and this smells right. In contrast, the system that these interactive theorem provers, there's a computer that really checks every one of these steps with soul-destroying accuracy and diligence.
Yes.
So this is where we are today, that we can express mathematical proofs, some of them non-trivial, and get them verified by a computer.
Yeah.
So this increases our belief in that this proof actually being correct, because
it's a matter of trust.
It's a matter of trust, right? It's a much more, so once a proof has been subjected to this kind of formalism, it's much more trustworthy than before. And as we observed, these proofs can be part of an argument for software being correct.
Yes. So the argument of software being correct, we can also be, well, in a sense, because we are doing logic, we might think that we are attracted by absoluteness. Logic is about absolute truth. But even for practical reasons, you may want to say, I want to have this extra verification. Like when you do a multiplication, you have easy ways to check whether your multiplication has a chance to be right. The things that we learned as a kid. Preuve par neuf is called in French.
Yes, something with nines in English. Yes, drawing out nines, something like that. Yeah. Yes.
But if we just want to develop a piece of software and make sure it's right, then what do? We write test cases. But the proposal by using the tool I have in hand is that, well, instead of writing test cases that are just points, why don't I write a test formula which is going to be true for a wide variety of input values, or which will be meaningful for a wide variety of values. And then I want to prove that this formula is always right. So I'm going to use logic for this. And this is a bit like testing, except that somehow my testing becomes symbolic.
Well, the goal is the same as testing, right? The goal is to improve the trust in a software system.
Yes.
And yeah, as you correctly observe, the standard way of software engineering is to subject there are many practices in software engineering. One is, I guess, peer review, that I publish my new piece of code and some other programmer looks at it and says, no, there's a mistake there. So that would be an easy case where we just can agree that I made a mistake. Or we can run the code and see that it does what it should. Yeah. Or we can run the code in a highly defensive way in the sense that I run the code deliberately trying to kill it by exposing it to inputs that may not even normally appear, yeah. but to run the code in some sense in a malicious way. I try to really kill this code. So a lot of industrial strength software today comes not only with the code that does what it should do, but also with enormous libraries of test cases that subject the code to these tests. So this builds a lot of trust, but it's not what you're advocating here, because you're not testing it by subjecting it to individual runs and seeing that they didn't fail.
I'm not advocating it. What I'm advocating is the method. You might say, yes, in your world, everything seems right, but is it useful for me? For me as a practitioner, and actually, this kind of experiment has been done. In the beginning of the 21st century, with a few colleagues, we decided to study the idea that a compiler for a programming language could be written completely using this approach. Mm-hmm. So they started in around 2002, and the main proponent of this approach is called Xavier Leroy, he's also a close colleague. and he designed a C compiler, which is called Coq'Art. So Coq'Art has been the language, the way we think that the language should behave, the way we think that the programs in this language should behave has been described completely formally. And there are logical formulas that say, whenever you write a program that has this shape, it should behave in that way.
So the semantics of the programming language C are more or less well defined here.
More or less, that is the book that defines C said at this place you can do whatever you want as a compiler writer. So the Coq'Art development made a choice, a specific choice for some of these instances. So it's not exactly the language C, it's a choice that is compatible with the definition, which was a piece of prose. Mm-hmm. Now, you have this piece of compiler, and then it has been tested. Been tested by people who didn't believe in informal methods any more than any other thing. What they did is they generated millions of small tests, and they compared all compilers, all available compilers on these tests. Mm-hmm. And so you have, if they don't agree, that somebody may make an error. And in that case, what you do is you go and look in the reference and you say, oh, maybe the disagreement is allowed by the language definition, or maybe the disagreement is not allowed, and one of them is making a mistake. And in doing this, after millions of tests, you can say, oh, one of them is failing less than the others. Coq'Art is failing less than the others.
Ah, but that's a great success. Right?
That's a success.
This is a good success story.
That's a practical success. You know, it's not just we finished the proof or something like that and it's been appraised by everybody. It's just a practical success. If you want to have a piece of software compiled and make sure that your compiler is not introducing a bug, then you have a good chance that using this one instead of using others is a good approach. The trust has been built not only by the fact that we have a logical description, and this logical description may be hard to read by anybody on the street, but we also have statistical evidence that's been produced by an independent team. So this is quite interesting. Mm-hmm. So this is why, you know, we have this connection with math, but we also have a deeply rooted origin in the need of making sure the compilers do what we want.
Or more generally, software does what we want, right? Because there are plenty of cases where it's not really so important that my Angry Birds program on my iPhone always does what it should. But there are cases where software is highly critical in the aviation industry, in the military, in surgery, and many other areas, or many of the small details where code today regulates a lot of our society, where we would like this to be really super precise, where we would like to bring everything we know as a civilization about trust and truth.
So trust is
into building software.
Trust is really important, and trust is something that has to be shared. So in this case, you know, we're talking about an industry. So this is a domain where people sell software and people buy software, and when you buy software, when you buy a house, you cannot necessarily go and look inside the walls to see if steel has been put at every place where it should be. It's not easy. So what you do is you make sure that it's been built by somebody who knows how to do it. And right now, until now, this is the way that software is developed. We just check that the companies that sells the software has the good credentials. But we probably can do better than that. We can not only say they have the good credentials, but they're also using the good methods. Mm-hmm. And somehow I'm advocating the idea that including this kind of proof with logical statements of what is expected in the development process may be useful. And using a tool, now there is a problem with the tool itself. You have to trust the proof tool. How can you be sure that the proof will not accept any fact as being true? No. So this is
you're moving the trust question instead of having to trust another mathematician. You're now having to trust a piece of software, a different piece of software,
yes,
to do the right thing.
And that piece of software may be also very complex. And how do I know that it's not going to accept a false statement at a place where it shouldn't? Mm-hmm. And in the case of the Coq system, you know, in the beginning, De Bruyne was saying, "Oh, we should develop these proof verification systems in such a way that they are so small, everybody agrees they are right." Mm-hmm. And for example, when Tom Hales, so this is another anecdote. Tom Hales published in the end of the 90s a proof of the Kepler conjecture, which is the conjecture that the optimal way to put spheres together is to put them like in a crystal. Well, and when he did this proof, he actually reduced a big number of cases and then wrote a program in C++ that checked all these cases using optimizations with transcendental functions and things like that. Right. And he had many of these tests, and he wrote a program, and then he said, my program checked all the tests, and this is correct. And when he wanted to publish the result, the mathematicians who were supposed to review the publication before it being accepted in a journal said, well, we trust all the mathematical reasoning that says that trusting this program will be okay. But we don't trust the program. We don't know that this program is doing the right thing. And so Tom has decided, okay, if they don't trust the program, I have to rewrite the program in a way that people can trust. And at that point, he decided to choose one among all these offers for interactive theorem provers, decided to choose one that was so small that there wouldn't be any doubt.
Even a mathematician could read that much code and be convinced that it does what it should.
Yeah, he could read that much code and do that. And so the system he chose for that was whole light. So I think we are facing this turning point. We need to be able to provide a tool that is trusted by a wide community so that we can then delegate our verification to that tool.
Building trust of increasingly complex systems by referring to the trustworthiness of a simple system.
So the case of whole light and the case of Coq are different in this respect. Whole light is developed by only one person, and for the Coq system, I'm trying to push in a direction where it's more of a community effort, and the community together is going to build up the trust.
So let me put my software engineering cap on. So in programming language, there's clearly has been an enormous effect, certainly for something like static analysis, which also started as an academic project. That is now part of many major programming languages and program environments, such that even non-theorists, so normal programmers, use these tools routinely. Actually, they can't avoid them because their compiler does this. So that's a huge success, I guess, from the formalist school that has had a big effect on software development and improved the quality of code a lot, reduced the error a lot, measurably. So do you see Coq and similar systems going in the same direction?
I would hope so, but I think there are hurdles to bypass because or to jump. The static analysis kind of tool is basically press button. You already know how to program. You write your program, and the system tells you, oh, but here you're going to go beyond the required interval of values or something.
Well, we have made it harder for the programmer. The programmer has to tell us what the type is and what the,
Yeah, but having to say what the type is in the beginning was not so much of a constraint, because frankly the programmer was making so many mistakes before that having this idea of writing types is a relief.
Turned out to be a relief
After
1 week, yes. After 1 week of programming.
I played with an Arduino 2 weeks ago, and I got burnt by a typing mistake right away. So I think it's a relief to have enough discipline in the language. It's like it's a relief to know that when you go and drive on the road, the other cars are going to be on the right side of the road.
Yes.
Okay.
Yes.
So you don't have to think about it anymore.
Okay. As soon as somebody invents that rule, everybody can see that's a good idea that we agree on.
So
that we all drive on the right side of the road.
And nobody's going to complain. Why do you impose this rule on me? So now I think the static analysis tools, their strong point is that the amount of extra energy you require from the engineer is quite low. Then you have an extra layer where you say, oh, we only are going to require the engineer to add more information about the logical statements that he wants to be satisfied at every point in the program. Like at this place, this variable should be within that interval, and it should be a prime, which is not an interval property.
Right, but some of these things, some of these assertions are also normal programmer routine.
Yeah. And so and then for this you can press a button and an automatic tool is called, and it solves most of the problems. But the point I had with the Knuth example with the array of prime numbers was that there will always remain formulae for which the automatic proof cannot be done for you. And for these ones, you will require the engineer to have way more competence in using a tool, way more training and way more competence. And for now, I don't know what is the economical model for that. Probably for very specific software where failure is really expensive, you want to have that happen.
And really expensive is death here, right?
It's not only that. If you're a company that sells modems, if you miss the output of your modem for September, you're going to miss the Christmas season. It's the death of your company.
It's the death of the company. Right, good. Yes, I'm more of a humanist there, but yeah, I see.
Yes,
okay.
But yes, death is a problem, and it's everywhere. But if we want to convince the industry to use this kind of technology, we have to have an economical case. It's less expensive to do it than to do something else, and the problem than to not do it.
Well, I could also imagine a case to be made not on an economical basis, but on a legal basis.
Yes.
That there could be highly critical software where we can require standards of software correctness that are way higher than what industry is economically incentivized to do.
Yes, in my dreams this happens. But if we look at the history of the software industry, this is not exactly what happened, because we have enormous companies that were built on the idea that they were shipping fast, but not necessarily correct. And if we want to impose today the law that you have to ship correct and not necessarily fast, they're going to say, you're going to kill our business. And they have enough power now that they can prevent that from happening.
Absolutely.
But if you look at a company like Microsoft, which produced this quick and dirty OS long ago, they are now very much convinced that they should be using this kind of technology.
Okay, that was the big picture thing. Let's just wrap this up by going back to pi and talk about the specific, because computing the millionth digit of pi is just a milestone where we can say that this is what we can do right now, right? And it's a nice, easily communicated milestone. But just talk a bit about what are the challenges here. So there's a formula going back to Mädchen or Machin. That one you proved correct?
The formula I used was from Gauss, actually.
Oh, Gauss. Yeah. Okay. So as a Gauss fan, I just assume that it's correct, but I guess it requires a proof as well.
Well, no, my objective was, of course, in that case, I used mathematics that was basically well known. But now you can consider that for another project, given industry comes up with an arbitrary theorem that is really new. Mm-hmm. And then there is a doubt that whether this theorem is correct. Yes. But still, because you believe in this theorem, you start to think you can make a piece of software that's going to change the life of millions of people. And it's important that you do it, and it's important that this piece of software is correct. So at this place, you have a new piece of mathematics that's been invented by a clever mathematician. You have a piece of software that builds on it, and you want everything to be connected right. You don't want to have a loose wire anywhere. So you would like to say, I'm going to make sure of that by connecting everything together. Because it's a new theorem, I don't necessarily know the perfect field of application, the domain of application. So I want to have a description of this domain application that shows that where I'm going to use it for my software is inside, precise enough. And there I'm going to need some mathematics. So this is what I wanted to do. I didn't want to work on necessarily very new mathematics, except that the Bohr1, there are new formulas to compute pi that have been produced very recently. And so we also verified one of these. So you have a new formula, you want to prove it correct, you want to make sure this is not going to be a cause for failure of your software, and then you want to connect that with the software. And you want the software to be relying on the real assumptions, the ones that that were verified. So you need to have a language in which you can talk both about the software and both about the mathematics that goes with it.
I guess what I want to ask is, if I was to sit down and just write a quick program that computed pi, I would take any of those many formulas from the shelf. I would then take an established library for doing computation with very high precision. I guess I would multiply everything with a few millions to get to have integers now, because I'm much more comfortable in computing with integers.
And the computer is too.
And the computer is too. So instead of computing the millionth digit of a number that is between 3 and 4, I want to compute the last digit of a number that is a million.
Yes.
Right. So I have computations in integers. I still have to add things that seem like fractions with very large numbers. But again, there are libraries for this. So I guess I could write up this code in an hour, and then I could just press return, and then it does the number crunching probably in a few seconds, and out comes the millionth digit of pi, which is 1. I guess I can even pipe this into Wolfram Alpha or some other online systems that does the computation for me or has cached the computation. I checked this. So just from a computing power point of view, we are currently able to compute pi to trillions of digits. I think 22 trillions of digits, and this is done in several different ways. So there's some trust in this 22nd trillionth digit of pi being correct as well, because different people have used different computers, different algorithms, and different formulas to arrive at the same digit. But this is expressly not what you've been doing. You've verified the computation of the millionth digit of pi, which involves operations on very large numbers.
Yeah, well, in fact, I didn't care about the million exactly. I used one number to show, but I cared about the algorithm.
Yeah.
So I could, tomorrow, if I want, I can restart this algorithm with another range and decide that the 10th millionth as given value.
Oh, because you're using a formula that does not require you to compute all the earlier digits? You can just...
No, that's not what I mean.
Okay.
What I mean is I have it's the algorithm that's verified.
Yeah. The algorithm is verified, yes.
So it can be run many times. It won't make any mistake anytime I do it. In some way, the people who just verify the algorithm against another implementation with a different formula, they do about the same. They have good chances that it works correctly. But I wish to have removed the statistical argument.
Yes,
and
exactly.
Looking at the algorithm.
Because these are two epistemologically, or if you want, more really different ways of increasing trust. One is computing things in different ways and seeing that the answer is the same, and the other is performing the computation in by an algorithm where every step has been subject to this extremely stringent analysis of the verifier.
Yeah, you could use two algorithms that are wrong, but do agree until a certain distance.
Right.
And in that case, I would have to trust that these two algorithms, the chances for you to pick two algorithms that are wrong but agree are too low. But in the case I'm saying the algorithm, at least the algorithm is completely verified.
Yeah. I guess what I want this is not just a question of number crunching, right? This is a question of writing proofs.
Yes.
I guess that's what I want, where I want to be. This is more of an
intellectual.
intellectual.
This is a question of writing proof, and in my case, what I wanted to illustrate is that we're advancing as a community in this kind of goal. That is, I'm reusing proofs that have been done by other people about how to make computations with big numbers. And I'm reusing proofs by other people about how to consider the whole of high school analysis,
yes,
or first year analysis for first university years analysis, real number analysis.
And when you say you're reusing proofs, you say you're reusing verified proofs in that system. So there's an increasing library of established math that we can build on.
There is a lot of if we're a lot of people who do automatic proof, they start from a clean table every computation. For me, I start from a library of established results. And somehow one of the efforts of the community efforts is to make sure that the proof system comes with a library of known facts that can be reused to make a lot of progress. So in this sense, I really feel part of a community effort. And there are two aspects. The Coq system itself should be easy to use, and the libraries that are provided with it should make it even more easy to do enough mathematics or enough algorithmics or enough computer, for example, there are a lot of people who are reusing this CompCert effort about the certified compiler because they want to study new approaches to correct programming with C, for example, also in concurrent settings and things like that. And they reuse the data that's already provided for this first project. So it's a community that's building up on its own advances.
Excellent. I think that's a great way of finishing the conversation, not the computation, the conversation. I learned a lot. Thank you, Yves, for coming.
You're welcome.
And thank you all for tuning in. You can find a lot of conversations of this type on casted.itu.dk. Bye.